An important key point or observation or the usefulness of non-dimensional equation is that the relationship between the key parameters in the problem are identified. So right from the beginning, we identify the important key parameters in the fluid flow that are playing active role and are important to the flow and will have an effect on the outcome, the resultant flow or the initial flow. And the other second advantage is that the number of parameters, when we have non-dimensionalized the equation, then the number of parameters sometimes are less than the number that was occurring in the original problem. So this is a great advantage, that you have to work with less parameters, less variables, making the problem simpler for any scientist or researcher. We look at an example whereby a given fluid flow situation is tried to represent in a graphic position. Because, as I have mentioned before, the fluid flow is a very visual subject, very visual phenomena, and therefore at times we need to represent it graphically. And how we can, by non-dimensionalizing the important parameters, how we can make its representation or graphical representation simpler. Here is an example. I have mentioned it more than once, that these examples are taken from the textbook that we are following, the Fluid Mechanics by Sengel and Simbala, that I have mentioned you before. And all these example number, equation number that are mentioned represent to what is given in the, because for simplicity I've just taken the photo, placed it here. The question: your little brother's high school physics class conducts experiments in a large vertical pipe whose inside is kept under vacuum conditions. The students are able to remotely release a steel ball at initial height Z0 between 0 and 15 meters measured from the bottom of the pipe. So from bottom upwards is the positive direction. And with the initial vertical speed W0, again that lies between 0 and 10 meters per second. So minimum speed is 0, maximum 10 meters per second. A computer coupled to a network of the photosensors along the pipe enables the students to plot the trajectory of the steel each time that it is thrown. The students are unfamiliar with dimensional analysis or non-dimensional techniques and therefore conduct several tests and experiments to determine how the trajectory is affected by initial conditions Z0 and W0. So they are looking at, if they change Z0 and W0, how the trajectory is affected. And we can imagine that it is affected. First, they hold W0 fixed at 4 meters per second and conduct some experiments at different heights of value 3, 6, 9, 12 and 15 meters. The experimental results then are shown in the picture that we are going to show you in a minute. The next one, they hold the height at Z0 equal to 10 meters and then conduct different experiments for W0 equal to 2, 4, 6, 8 and 10 meters per second. Then they plot these graphs also. And our job is how to combine, first, if we were to non-dimensionalize the parameters that are playing role in the equations, then is it possible to simplify the problem? And we see that it is the condition, it is the situation. So this is the situation of the problem that I have already explained to you, but it is written. Now, if we look at the trajectories in the first situation, where the experiments were conducted with the initial velocity of 4 meters per second, and the height is also varied, as you can see in the graph, from 3 meters, 6 meters, 9, 12 and 15. The initial velocity was W naught equal to 4 meters per second. When the trajectory was plotted, then you can see, and these are dimensional variable at this point in time, and then the trajectories look like this, that if the first one is dropped at a height of 15 meters, then it falls away and comes to this point. It takes this much time to come to the bottom. And if it is thrown from a smaller height, it takes a much smaller time to come to the ground. And when the Z naught is fixed at 10 meters per second, and then they keep changing it to 8, 6, 4 and 2, but with different velocity scale. So then what happens? So this time the steel ball is thrown from a 10 meter height, but with velocities 2 meters per second, 4 meters per second, 6 meters per second, 8 meters per second and 10 meters per second. So 3 different values, whereas earlier the velocity was 4 meters per second, and then the heights were 3 meter, 6 meter, 9 meter, 12 meter and 15 meter. So that problem was tackled in a slightly different way, and this is tackled in a slightly different way. Here the height is kept fixed, but the velocity is changing. And then what do we see? We see the trajectory as this. Now, how to combine the two plots? How to combine the two types of trajectories that were there? In one case, the height was kept fixed, and in the other case, the velocity was kept fixed, and the other parameter was varied. So we did that by introducing the Froude number, by calculating the Froude number in each case, and when we plotted it, then we observed that both the set of equations, both the set of experimental data could be plotted in just one graph. And you can see the green lines and the red lines showing the different scenarios, but on the same graph and on the same scale. So what is happening? Making things easier for us, rather than having two graphs, we are plotting the data into the same graph and looking at it. And so the trajectories of a steel ball falling in a vacuum, they are non-dimensionalized. And you can see that how the picture look like, how the speed, the fall, they behave when the Froude number is small or it is increasing. And similarly, what happens if the height is increased, and in this case the non-dimensional height, and similarly the time is also non-dimensional, but you can see that how these things are changing just as the Froude number increases.